Welcome back. We start our next lesson today, and we are going to revisit congruence class equations and do a few more examples before we move on to the next topic. So it will be familiar to you again. The first problem I have chosen is to find the multiplicative inverse of 5 in modulo 47. And that means I need to solve this equation. 5x is equal to 1 for x, because if I know x, then that's the multiplicative inverse of 5. So to solve that, we use our Diophantine equation, and we write the Diophantine equation for this. 5x is equal to 1, and then 5x minus 1 is some 47y for some y. Move that over, and that's our Diophantine equation. So I want to find solutions to this. Now, so we know that a is equal to 5 and m is 47 and c is equal to 1. For this Diophantine equation to have solutions, we must have the greatest common divisor of a and m be dividing c. So that's 1. 1 divides any number, so we have one solution, therefore we know that the inverse is unique. So we know there is an inverse. Of course, 47 is a prime number, so we had that result earlier also. So there is an inverse, but which one from these 47? So to find that, let's use the extended Euclid algorithm like what we did earlier. And so instead of considering this equation, we will consider the alternate equation, because we want the larger number up front and I don't want any negatives. So I'm going to look at 47u plus 5v equals r. And then we in our table of extended Euclidean algorithm, the first two rows are always the same, r1 and r2. And then R3, we need to find Q3 first. So to find Q3, we divide the two R values, and it's 9 point something. So my R3 is Q3 is 9. That's the flow of that number. Once I know Q3, I can find R3 using R1 minus Q times R2. So you will get 1. You get negative 9, and 47 minus 9 times 5 is 2. So there you go. That's your first step. We still haven't hit the GCD of 1. It's still 2. So therefore we'll have to do another loop here. So find Q4, and Q4 now is the flow of 5 divided by 2. So we have to divide 5 by 2 to get Q4, and that's 2.5, so Q4 is going to be 2, because that's the flow. So once I know Q4, I can therefore write R4. So I subtract from R2, Q4 times R3, so 0 minus negative 2 is a negative 2, 1 multiply this, that's a negative 18. So 1 minus 18 is a positive 19, and 5 minus 4 is 1. That's GCD. So therefore we can stop there, because we hit our GCD here, and we can therefore write, so 47 times negative 2 plus 5 times 19 is equal to 1. And now we can compare our two equations and see what x should be. And by inspection you will see that I'm comparing this equation to that, and you will see that x should be 19. Just by comparison, x should be 19. Y is equal to 2, but we are not interested in y. We were solving for x, therefore x is 19, therefore we have 5's inverse is 19. You can always, of course, check if you use a calculator and check 5 times 19. You will see that 5 times 19 is equal to 1 in congruence modulo 47. So that's how you can find an inverse. First you need to, of course, make sure that the inverse exists. If the inverse exists, then this method will get you the inverse. Okay. That brings us to another interesting problem from history post a long time ago. It comes from China. It's called the Chinese remainder theorem, and it's asking us to solve a pair of equations, not just one congruence equation, but a pair of equations simultaneously. So there's a theorem that helps us to solve this. So let a1, a2 be any two integers, and if GCD of m1, m2 is equal to 1, that means m1 and m2 are co-prime, they have no common factors except for 1, then the simultaneous linear congruence equations n equals a1 mod m1 and n equals a2 mod m2 has a unique solution in mod m1 and m2. Now we are solving for n, that's what we want to find. What is the n that will satisfy both these equations? And when we are working in mod m1 and m2, our solution comes out in the mod m1 m2, in the product. So here's an example. Suppose I want to solve this. I want to find n that will satisfy this equation in mod 5, and the same n must satisfy it in mod 11 as well. First thing is to check whether there is a solution. So if I look for the co-primeness of m1 and m2, m1 and m2 are prime numbers anyways, so they are co-prime, therefore we know that we have a solution. So let's go and try to find this solution. So the first equation gives me that n is related to 2 in mod 5. So I can get an equation that looks like n is equal to 5x plus 2 for some integer x. The second equation says n is also related to 9 through modulo 11. So n and 9 are also related, and therefore I can get a second equation that looks like that. So using the two equations, I can get myself a Diophantine equation. 5x plus 2 is 11y plus 9, and I have 5x equals 7 plus 11y. Now we need to solve this Diophantine equation first, because if I can find x, then I can use it to find my n. To solve this Diophantine equation, I need to check whether it has solutions. So a is 5, and m is 11, and c is 7, and the requirement for this Diophantine equation to have solutions is that the GCD of am must divide c. Now GCD a and m are co-prime in this example, so that's equal to 1, so it does divide c. 1 divides any number, therefore d divides c, and we have a solution. Can write d divides c. So that's the check that you need to see whether it has a solution. So let's go and, we know it has a solution, let's find the solution to the Diophantine equation, find that x, and then we can find the n from here. Okay. To solve this equation, let's use the extended Euclidean algorithm, and instead of solving this equation, I'm going to look at the alternate equation, because I want my first number to be the bigger number and I do not want negative numbers. So 11u plus 5v equals r. That's what I'm going to solve. The first rows are easy. You can see the row 1, row 2. We put all the values into that, and I can find my q3 first by taking the flow of 11 divided by 5, which is equal to 2. Now let me complete this table. So R3, I subtract from R1, Q3 times R2, and my R3, row 3 will look like 1, negative 2, and 1. And that's my GCD, so therefore it's completely done.